Hello and welcome to Cognito Key. Today, we are going to pull back the curtain on one of the coolest tricks that makes your computer so ridiculously fast. It's a concept called pipelining, and trust me, it's the secret sauce inside every single modern processor.
So, to really get this, I want you to think about something. What on earth could a giant, noisy car factory possibly have in common with the tiny, super complex brain inside your computer? I know, it sounds a bit random, but the answer, well, it's pretty fascinating.
It's the assembly line. Seriously. Think about how a car is built. It moves down a line, right? At one station, they put the chassis together. At the next, they add the body. Then the engine goes in, then it gets painted. But here's the clever part. The workers at the chassis station don't just sit around waiting for that first car to be completely finished. Nope. The second they're done with their part, they immediately start working on the very next car's chassis.
And that right there is exactly what pipelining does inside your computer's processor. It's the same idea. It takes a big job, like executing a command, and breaks it down into smaller steps. Then, it processes a bunch of these commands all at once, just like that assembly line. This whole process massively improves what we call throughput, which is really just a fancy way of saying your computer gets way more work done in the same amount of time.
Okay, so let's get into the nitty-gritty. How does this digital assembly line actually work? Well, every single instruction your computer has to deal with gets chopped up into a series of smaller, much more manageable steps. And usually, we're talking about 5 key stages.
First up, we've got instruction fetch. You can think of this as just grabbing the right recipe from a cookbook. Next is instruction decode, where the processor actually reads the recipe to figure out what it's supposed to do. After that comes operand fetch. This is where it gathers all the data it needs, the operands. These are basically your ingredients. Then you have the main event, instruction execute. This is where the actual calculation happens. And finally, operand store, where the final result is saved.
Okay, now here comes the really cool part, the magic of it all. Pipelining overlaps these stages. So picture this, as the first instruction moves from the fetch stage to the decode stage, a brand new instruction immediately jumps into the fetch stage. Then, as that first one moves on again, the second one moves up, and a third one enters the line. See what's happening? The processor's hardware is never just sitting there twiddling its thumbs. It's always busy, constantly juggling different parts of different instructions all at the same time.
But, of course, there has to be a rule to keep things from getting chaotic. And it's a simple one. No 2 instructions can be in the same stage at the same time. So you can't have 2 different instructions trying to get decoded in the exact same clock cycle. It's just like on a real assembly line. You can't have 2 cars in the painting booth at once. This one rule is what keeps the whole thing running smoothly, with no collisions.
Now, you've probably guessed that not all pipelines are created equal. This whole concept has evolved over time, and there are a few different flavors of pipelining out there. But for now, let's just focus on one really important distinction that shows you how flexible this idea can be. So you've got static and dynamic pipelining. A static pipeline, think of it like a factory that's hyper-specialized. It only makes one thing, let's say a specific type of screw. It's unbelievably fast and efficient at that one job. A dynamic pipeline, on the other hand, is like a much more versatile factory. It can switch things up on the fly, making screws one minute, then bolts, then nails. It can handle a bunch of different functions at the same time, which makes it way more flexible.
But what happens when this perfectly smooth, super efficient assembly line hits a problem? Because even the best laid plans can go wrong, right? In the world of pipelining, we call these little hiccups hazards.
So what's a hazard? Well, simply put, a pipeline hazard is anything that forces the entire assembly line to just stop, or as we say in the biz, to stall. This means for a tick of the clock, or maybe even a few ticks, the whole operation grinds to a halt, while it waits for the problem to get sorted out. Let's look at the 2 most common ones you'll run into.
All right, hazard number 1 is called data dependency. This is a big one. So take a look at the code here. The first line, add, is telling the computer to add 2 numbers, R1 and R0, and save the answer in a spot called R2. Simple enough. But look at the very next line, the sub instruction. To do its job, it needs the answer that's supposed to be in R2. You see the problem yet?
Here's the issue. It's all about timing. The sub instruction is already chugging along the pipeline, and it needs the answer from add. But the add instruction hasn't even finished its job yet. It's like asking for a cake before it's even out of the oven. To keep from getting a completely wrong answer, the whole pipeline has to hit the brakes. It stalls, just long enough for the right data to be ready. Okay, on to our second big hazard, branch delay. Now remember, pipelining is so fast because the processor is always grabbing the next instruction in line before it even needs it. But what happens when an instruction isn't just a simple calculation? What if it's a branch? A branch is basically a fork in the road. It's a command that tells the CPU, hey, forget the next thing in line, I need you to jump over to a totally different part of the program right now.
Well, you can probably guess what happens. The pipeline, trying to be efficient, has already grabbed the next few instructions that it thought it was going to need. But now, thanks to that branch, all that work was for nothing. Those instructions are totally useless now. They all have to be tossed out. The entire pipeline has to be cleared out, or flushed, and then refilled with the right instructions. And all of that, as you can imagine, causes a delay.
So, after hearing about all these stalls and hazards, you might be thinking, is this whole pipelining thing really worth all the trouble? And the answer is, oh, absolutely yes, 1,000 times yes. Let's talk about the massive payoff.
Yeah, even with the occasional stall, the benefits are just huge. Pipelining is what allows for real, true parallel processing inside a single processor core. But here's the absolute game changer. The main thing to remember, once that pipeline is full and running, a brand new instruction can be completed on every single tick of the processor's clock. That is an absolutely revolutionary leap in speed and efficiency.
Just to put this into perspective, modern processors can execute billions of instructions every single second. Billions! A number that big would be completely impossible without the incredible efficiency of an assembly line. Pipelining really is a fundamental cornerstone of all modern computing. And it just goes to show you how a simple, really elegant idea can change absolutely everything. Pipelining took computing from a one-thing-at-a-time task to a massively parallel one. Which leaves us with a big question to think about. What do you think is the next assembly line idea that's going to completely revolutionize computing speed? And hey, if you found this explainer helpful, please do us a huge favor and hit that like button, share it with a friend, and subscribe to Cognato Key for more. Thanks so much for watching.